In Part 18, I finished the discussion on acid-base titrations. In this presentation, before going forward, the subject of reduction and oxidation reactions, labeled as redox reactions, must be introduced prior to the precipitative, electro-gravimetric, and other forms of titration is presented. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Oxidation numbers go hand in hand with redox reactions, which allows for redox titrations. Oxidation numbers are simply numbers that reflect the total number of electrons that an atom may gain or lose when forming a chemical bond with another element. The oxidation number is a reflection of the ability of a species to acquire, donate, or share electrons forming the bond. There are a few rules that govern the assignment of the determination of the oxidation numbers. There are 10 rules of which govern the determination of an oxidation number. Rule number 1. Oxidation numbers for atoms and substances, which are neutral, will have an oxidation number that equals 0. Examples are O2, O3, P4, even S8, all of which are stable covalent bonds in most cases. Note, oxidation numbers are not formal ionic charges. The second rule has an exception to the rule number 1, and that is that simple ions will have an oxidation number equal to its ionic charge. When these atoms bond ionically, the oxidation number of the molecule formed must equal 0. Also note that the oxidation number, when added to the reaction equation, the plus or minus symbol charge is put in front of the element or compound, whereas the symbol for the ionic charge is placed behind the element or compound. Examples are shown. Rule number 3 simply states that any hydrogen atom that is bonded ionically with a nonmetal atom or polyatomic ion, such as methane and ammonium, will always have an oxidation number of +1. However, rule number 4 states that any hydrogen atom that is bonded covalently to a metal element, it will have an oxidation number of -1. Note that hydrogen is the only element that can exist having either a positive ionic charge of 1+ or a negative ionic charge of 1-. Examples as shown are lithium hydride, sodium hydride, calcium hydride, and calcium aluminum hydride. Rule number 5 states that all the elements in the group 1 of the periodic table will have oxidation numbers that equal +1. However, if the group 1 elements bond with nonmetallic elements, the resulting molecule will have an oxidation number that equals 0. For example, lithium combining with nitrogen. Lithium will have an oxidation number of +1. Nitrogen has an oxidation number of -3. Both species will have the respective ionic charges as both are simple ions. Therefore, the molecule formed will have an oxidation number that equals 0, as it will take 3 lithium atoms to form the molecule. Therefore, 3 times the +1 plus the -3 will equal 0. Therefore, lithium nitride has an oxidation number of 0. Now, Rule 6 is basically the same as Rule 5. The difference is that the group 2 elements in the periodic table will have oxidation numbers that equal +2. Note that rules 5 and 6 also follows rule number 2 for simple ions. Rule number 7 is a little different, as it relates to diatomic oxygen molecules and peroxides. Oxygen atoms have oxidation numbers that equal -2. But as a diatomic molecule, O2, or as in hydrogen peroxide, or in sodium peroxide, for example, the oxygen will have oxidation values of -1. Rule number 8 is similar to rule number 2. It states that the sum of the oxidation numbers in a neutral molecule must equal 0. Whereas in rule number 9, which states that the sum of the oxidation numbers will be equal to the ion charge of a non-neutral polyatomic ion, such as SO4, a sulfate ion. An example is shown where the oxidation number for the sulfur ion in the sulfate molecule is +6. Taking the +6 and adding to the -8 equates that the sulfate will have a -2 charge, or oxidation number of -2. Rule number 10 is in reference to neutral polyatomic ions such as sulfites, SO3, and sulfides, SO2. These polyatomic ions must have oxidation numbers of 0. Chlorine trifluoride has no oxygen molecules, and therefore it is a neutral molecule. As shown, it has 1 chlorine atom and 3 fluorine atoms. Since there are 3 fluorine atoms having ionic charges of 1-, the oxidation number must be -3. Chlorine trifluoride, being a neutral molecule, its oxidation number must be 0. Therefore, the oxidation number of the chlorine ion must be +3. Sulfate has oxygen atoms. Unlike sulfides and sulfites, this molecule is non-neutral. Its oxidation number is equal to its ionic charge. There are 4 oxygen atoms having ionic charges of 2-, gives a total of -8. The sulfur atom has a 2- ion charge. However, there are 4 oxygen atoms. The coefficient of 4 is added to the sulfur atom as shown. The -8 plus 4 is equal to -4. Dividing the -4 by the sulfur's coefficient of 2 equals -2, which is the oxidation number for the sulfate ion, as well as its ionic charge. The same method applies to the chlorine tetroxide. The oxidation number for the oxygen is -8. The -8 plus 4 is -4. The -4 is then divided by 4, which equals -1. Therefore, the oxidation number for the chlorine ion is -8 minus the -1, which equals -7. As an add-on to the slide, there is a personal trick that someone posted and circulated on social media. Most, but not all, polyatomic ions form acids. The trick is associated with the hydrogen atoms in the molecule. Each hydrogen atom has an oxidation number of 1. As for the sulfate ion in sulfuric acid, HSO4, knowing the compound's oxidation number, the sulfate ion's oxidation number is -2. As shown, the columns on the periodic table represents different groups of elements. Each group has its own number, from 1 to 18. There are 2 more tricks that the individual posted and circulated. Using the periodic table, all one has to do is find the element and note which group it is in. To be more specific, is the group number an odd number or an even number? Now each box represents a set of 2 groups, even-odd, even-even, or odd-odd. Using nitrate, NO3, for example, nitrogen is in an odd group, whereas oxygen is in an even group. Referencing the even-odd box, it shows the ion charge of -1. For the oxidation number, one needs to know if the polyatomic ion is neutral or not. The only exception to these cheat sheets is the phosphate and phosphite ions. They do not follow the simple trick. However, their oxidation numbers will always be -3. This presentation is the beginning of the discussion on redox reactions. This presentation focused on oxidation numbers. Oxidation numbers go hand in hand with redox reactions, which is the sequel to this presentation. I hope that I was able to present this short presentation in a manner that anyone without a chemistry background would understand. For those of you that have been following along with this educational series, I hope that this presentation entices you to view Part 20 when it is published, and Part 21 will follow, focused on the how-to and why for the redox titrations. If you found this presentation useful and interesting, or if you know of someone who may benefit from this presentation, please give it a like and a share, and maybe subscribe to the channel. It is my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.